So hi friends, so today we are going to see optical encoder. So now agenda of this presentation contains rotary encoders, information about rotary encoders, then optical encoders, then various types like incremental encoder, absolute encoder. So all these things we are going to study in this presentation. So firstly, let us see rotary encoders. Rotary encoders are non-contact optical devices used for converting the angular position of a rotating shaft into an analog or digital data code. So basically encoders are used, or rotary encoders are used to measure the angular position of rotating shaft. So the output may be in analog or digital form. In another words, they convert mechanical movement into electrical signal or digital signal. Next type is optical encoders. So all optical encoders work on the same basic principle. Light from an LED or infrared light source is passed through a rotating high resolution encoded disk that contains the required code patterns, either binary or gray code. Then photo detectors scan the disk as it rotates, and an electronic circuit passes the information into an digital form as a stream of binary output pulses that are fed to the counters or controllers, which determine the actual angular position of the shaft. So the working and construction we are going to see in our next slides. So now types of encoders are basically there are two types: incremental encoders and absolute position encoders. So let us see first one, incremental encoders. So now incremental encoders are also known as relative rotary encoders, as the simplest of two position sensors. Their output is a series of square wave pulses generated by a photocell arrangement as the coded disk, with evenly speed transparent and dark lines called segments on the surface, moves or rotates past the light source. The encoder produces a stream of square wave pulses, which then counted indicates the angular position of the rotating shaft. How? Let us see in next slide. So here you can see the construction. This is the rotating shaft which is attached to the moving disc, right? And this moving disc has the slits you can see here. These are the various slits at various angular position. Okay, so this is the light source or LED, which will pass the light through this slits in the moving disc, and the light is collected at the light receiving elements or light receiving sensors here. So at the sensor, the signal will be in the form of square wave. You can see here A, B, C, and this is the signal controller. So depending upon the position of this slit, signal will get generated at this particular sensor side, and these signals, output signal A, B and Z, they are converted into the angular position of the shaft. actual value of angular position of the shaft. Okay, so here you can see here, this is another type of incremental optical encoder. So this disk is rotating clockwise direction CW. So you can see here light sources or LED. So light will pass through these slits, and these are the light detector receivers. So which receives signals. So now this is for counterclockwise. We can get the wave here. Since there are two sensors or two light sources, we will get two receiver signal here, on and off. So this is in case of counterclockwise, and this is clockwise. So that was the incremental. Then let us see absolute optical encoders. So the absolute optical encoders are more complex than this quadrature encoders. They provide a unique output code for every single position of a rotation indicating both position and direction. So difference between incremental and absolute optical encoder is that absolute optical encoders will indicate both position and direction. Their coded disk consists of multiple concentric tracks of light and dark segments. Each track is independent with its own photodetector to simultaneously read a unique coded position value for each angle of movement. The number of tracks on the disk corresponds to the binary bit resolution of the encoder. So, a 12-bit absolute encoder would have 12 tracks, and the same coded value only appears once per revolution. So how we are going to see in next slide. So since we have these four segments, you can see here, first, second, third and fourth, four segments or four concentric circle. That's why it is called as 4-bit binary optical absolute encoder, right? So we will be having four light sources or four LEDs at one end, and we will be having four receivers to receive the light source or capture the lights. So that is shown here. So likewise, here you can see the output, which will be in binary format. So we will get 4 bits here. They are either in 0 or either in 1 format, since they are binary. So 4 bits, and here these bits are converted into displacement in angular position. So this is how 4-bit binary optical absolute encoder works. So this is another type of absolute optical encoder. Now it is 8-bit optical encoder. Since there are 8 segments or 8 concentric circles are there, so it requires 8 light emission diode and 8 sensors to detect the light. Here you can see the shaft whose angular position is to be calculated, that is connected to this disc. So this is also called as a local plate, and this is the fixed slit. So we'll be having photo transistor, or you can say a sensor. So for each sensor we will get output in the square form. Likewise we will get the output, and that output is converted into displacement or the angular position of the shaft. Applications. Typical applications of absolute optical position encoders are in computer hard drives and CD and DVD drives, where the absolute position of the drives read write heads are monitors, or the in printers or plotters to accurately position the printing heads over the paper. So these are the various applications of optical encoders. So if you can see here, this is the 8-bit absolute optical encoders. This is the 4-bit binary optical absolute encoder, you can see here. And this is the 2-bit incremental encoders.